Hello mates, in the previous video we just introduced the first equatorial system, and this is the diagram that we came up with when we finished. When we labeled everything on the diagram that is useful to us: the origin, the celestial equator, the horizon, celestial axis, and the observer's meridian. So now we are going to see how to define the angles. So far I've been favoring people who are in the northern hemisphere. Let me favor people who are also in the southern hemisphere. I'm in the southern hemisphere in Johannesburg, so let me favor myself. So I'm going to give a situation that is where someone is in the southern hemisphere. If someone is in the southern hemisphere, the visible pole will be the southern celestial pole. So let's say this is the southern celestial pole. I'm saying the visible one because that is the one that will be above the person's horizon. So north celestial pole. This one will be the zenith, and here there will be the nadir. I'm not going to draw in the horizon because in this system the horizon really does not matter. That it matters because it's the one that tells us which origin to use. But if I draw it in, it might be a bit complicated. The diagram might become a bit complicated. So I'm just going to leave it out. But just know that the horizon is going to be perpendicular to this axis. So the horizon is here, is the half line of let me just put markers that are going to mark where the horizon is. So the horizon is going to be there. That's where the horizon is going to be. So now this south celestial pole, if we connect, we're going to have an axis as always, and perpendicular to this is going to be our celestial equator as we discussed, and it goes all the way to the back. And this will be the core of our, or where the earth is, the core of our celestial sphere. If you remember in the beginning, in the first video of our celestial sphere, we said the observer is always at the center of the celestial sphere. So this is where the observer is on earth, so we are going to call it our point C. Now, since this is the horizon, we said the origin is, and yeah, this is the celestial meridian, because that's the line, that's the circle that connects the south celestial pole, zenith, north celestial pole, and the nadir. So the outside circle is the celestial meridian. And we said the point that is the point where there are 2 points there are 2 points where the celestial equator is going to cut the celestial meridian. This point and this point. That's where the equator, the celestial equator, cuts the celestial meridian. And the point that is above the observer's horizon is going to be our origin. So this is our origin, right? That is going to be our origin. So since that is going to be our origin, let's now put angles. Let's imagine a star that is here. We are going to call this star S, and we want to pinpoint that star. What we are going to do, just like in the other systems that we've done before, in this system we use things called hour circles. In the other systems we're using the vertical circles and the lines of longitude. But in this system, the first equatorial system, we are going to use an hour circle. So an hour circle is defined as the great circle that connects the south celestial pole, that goes through the star and cuts the celestial equator, and then connects with the north celestial pole. It's going to be a great circle because it's going to go at the back, and it's going to contain the axis, and it contains the center. So it's going to be a great circle. So this circle that passes through the star and connects the two poles like this is the hour circle for that particular star. So that's the one that we are going to use to measure where this thing is away from the origin. I didn't state this like I did before, but our x-axis is going to be the celestial equator. That is going to be our x-axis, the celestial equator. So it means we need to find our point M on the celestial equator, where we can measure our x angle. So can you see this hour circle meets the celestial equator at this point, and we are going to call it point M. So now we can measure our angle OCM. We can measure our angle OCM this angle right here called OCM, let's define it. It's OCM. OCM measured from the celestial meridian, is measured from the celestial meridian through west. Through west is called what? From 0 degrees to 360 degrees is known as the hour angle of S. So now I think I've actually made a mistake here. This is one thing that you should never make a mistake on. Where is your east side? Where is your east side? This is our what? Our west, and this is our east. You see, this is going to be the eastern side, which is outside the paper, and what is inside the paper, that is going to be the western side. So now our angle, let's define our angle. Our angle is the what? Is the angle from the celestial meridian to the hour angle of the star measured through west. Please, I emphasize, it's measured through west. This you should never forget. Our angles are measured through west. So we are going to measure our angle through west like this. And then coming here, we are going to measure our OCM. So OCM measured from the celestial meridian is going to be measured from the celestial meridian like this through west from 0 to 360 degrees is known as the hour angle of S. So this is going to be our hour angle of S. And then we have another angle MCS. We have another angle MCS. Why am I saying MCS when I haven't defined it? MCS is basically the elevation of this star S above the celestial equator. So that's going to be our MCS. Just like we do for the other systems, the elevation above our x-axis is the angle that we also need to define where exactly on that hour angle is the star. So we need our MCS. Our MCS measured perpendicular to the celestial equator from 0 to 90 degrees north or south. 0 to 90 degrees north or south is known as the declination. So this thing is now called the declination. And these names, you have to know these names off by heart. You have to know these names. So in the first equatorial system, these are our coordinates. Our coordinates are our angle and declination. And declination is given a symbol, is denoted by this symbol. That is the denotation of what? Of declination. So now this is what we are going to. These are what? These are our definitions of our angle and declination, and I hope I haven't confused anyone on that part. That the hour angle, you just draw an hour circle. You draw an hour circle through the star, and then you measure from this celestial meridian, or from O, you measure through west the angle that our circle is going to make with the point M. That is the angle that we are concerned with, isn't it? Concerned about. So now when we have our OCM, it's called the hour angle of S. And then the elevation above or below the equator is called the declination. And it's given this symbol. I think it's a delta. I'm not quite sure, but I think it's a del or delta symbol. I'm not quite sure about that one. But just know this symbol, yeah. So now we are going to now we are just going to state important notes here before we get into an example of seeing how to apply this. We're just going to state a few notes. Can you see that the celestial sphere rotates like this? It rotates like this because our Earth rotates like this, right? With the celestial equator. It rotates about the celestial equator. Just like on Earth, imagine this is our geographical equator, and this is our point on Earth. This is the point on Earth. So imagine this is our geographical equator. When the Earth rotates, can you see that the latitude of this point, the elevation above this equator is not changing because it's just rotating like this. The Earth is just rotating about an axis. It's just rotating about the axis, and the elevation above or the latitude is not going to change. On Earth it doesn't change, obviously, because the Earth is just fixed like that. Let's look at our celestial sphere. Imagine that our star was this. Okay, this is our star. Okay, let's get the orientation right. Houston, what are you doing? Okay, let's forget about this star. Let's imagine. Let me draw another star to match up the orientation here. So imagine this is going to be our star at that point. Since the celestial sphere rotates because of the Earth, and it rotates about a fixed axis that does not change because the Earth's fixed axis, because this is just an extension of a fixed axis of the Earth, it basically means this orientation is not going to change as the celestial sphere is what is rotating. So it's just going to rotate the same way. So let's rotate it the same way. I hope you see something interesting there. The star is going to rotate, maintaining its elevation above the what? Above the celestial equator. It's going to maintain its elevation as this is rotating about that fixed above that fixed axis from SCP to NCP, that's celestial axis. So can you see, no matter how it rotates, this one maintains its what? It's let me say height. Its height above the what? Above the celestial equator. So basically what I mean is this star is going to rotate in such a way that it is always the same height above the what? Above the celestial equator. It is always the same height above the celestial equator, but it's not exactly height. It's called declination. So it means as this star is rotating, since it's maintaining its distance from the celestial equator, it basically means the declination of a star remains constant with passing time. As the Earth is rotating or also forcing the celestial sphere to rotate, the declination remains constant with time. So here, declination is constant. But can you see something that is happening now? When the celestial sphere rotates, imagine now the star is here. If the star is now there, we are going to draw our circle like that. And now our M is now there, which means our angle OCM has increased as the celestial sphere rotated. I hope you see what I mean. As the star is now here, our M is now there, so our OCM has increased from this to include this. So it's now OCM all the way there. So basically, OCM increases uniformly from 0 to 360 in one revolution of the sky. In one revolution of the sky, it goes the hour angle increases from 0 to 360. Hence, our angle is known at one instant. It can be calculated at another interval if it is known at one instant, because we have the period, the revolutions and stuff like that. We're going to get into good examples, but this is an important point, that what our angle increases from 0 degrees to 360 degrees with passing time, but the declination, the height above the celestial equator, remains constant as it is rotating, but the what do you call this, the hour angle does not remain constant. So that is a very useful note. Another, I think this will be our let's see, I think this will be our last note before an example, but it's a very useful note. Now, can you see this star? Let me show you. Let me bring it back. Is this the star that we're dealing with? Okay, let me bring back the star. Can you see this star? This star is going to cross. This star is going to cross the observer's celestial meridian twice. It's going to cross here the celestial meridian at that point when the celestial sphere is rotating at this point, and also at this point. So it's going to cross at those 2 points, right? So it crosses, goes at the back, and then when it's coming into the front, it crosses again the celestial meridian twice. Once above. So can you see there's one point above the SCP, and then there's another point that is below the polar axis. So there's a point that is above the polar axis, and there's a point below the polar axis, isn't it? When it crosses above the polar axis, it is called upper transit. This is called upper transit. So upper transit is a situation where the star crosses the celestial meridian above the what? Above the celestial axis. That is what is called upper transit. So now, when it crosses the celestial meridian below the celestial axis, this is called the lower transit part, or the lower transit point. It's called lower transit. Oh, sorry, when I wrote upper transit, you didn't see where the upper transit was happening. This is where the upper transit is happening, because it's crossing the celestial meridian at this point and also at this point. This is upper transit because it's the point that is above the celestial axis. So this is upper transit, and this is the lower transit because it's the point that is below the celestial axis. This is the celestial axis. So this one is going to be lower transit. So now, with that point in mind, you can take upper transit as the maximum height a star will reach, because this is going to be my horizon, isn't it? This is going to be my horizon. So since that is going to be my horizon, can you see this star is going to above my horizon is going to be having this height here. When the star is there above my horizon, this is going to be the height. When it's there, this is going to be the height. When it's there, this is going to be the height. So upper transit is the maximum height above the horizon that the star will ever attain. Because as it goes to the back now, it's starting to fall with respect to our horizon. So it's now starting to fall. That's when you see now the star is now getting closer to our horizon, or you see the sun setting. It's the same situation. Imagine this is the sun. When it goes up, now it's midday. It's because it's now at upper transit. It's now crossing your celestial meridian. It's now at its maximum height. But then when it starts setting, when the sun starts setting, it's because now it is coming down like this. With respect to your horizon, it looks as if the star is now what? Is now coming to your horizon, and then when it goes below your horizon, you cannot see it anymore. And now, with respect, when we're talking about the sun, we say the sun has set because it has gone below your horizon, and then it will reach its lower transit. But we cannot see it in lower transit because with this particular star, we can see it in lower transit because of what? And because of it being lower transit or happening below our horizon. And then when it comes here, when it comes to this part here, it's now at our horizon, and then we say, the sun is now rising. It's because it's now gaining height above our horizon. So now we can see it more and more and more and more until it reaches upper transit, when it's crossing our celestial meridian at its maximum height, and then it sets again. So that is another point where we have upper transit and lower transit. In the next video, we are going to do examples, and when we do examples, we are going to see where these upper transits come in. So stay tuned for those examples of the coordinate system and the upper transit.